Okay, so once again, welcome to day 2 of the IBM workshop on the informational lens. I think we had a wonderful roster of speakers yesterday. They were all quite thought-provoking talks, and the Q&A and discussion sessions were great as well. Remember, if you still have questions, you're free to ask those questions on Slack. So today's topic will shift from quantum computing to more conventional mathematics and computer science. And again, if you have questions for any of the speakers, including myself in this opening talk, go to the Slack channel that from yesterday, or if this is your first day attending, you should have gotten an email with this, the name of the Slack channel. So let me give you a little bit of a preview of today's talks. So the first speaker will be Nicolas Gisin, and his talk will be about indeterminism in physics and intuitionistic mathematics. Nicholas will talk about a new mathematical framework he has been developing for describing physical processes based on intuitionistic mathematics. He'll describe a compelling view of real numbers, themselves time-evolving processes that are the result of measurements or calculations, the successive bits of which are revealed probabilistically over time. Following that, Doron Zeilberger will be talking on the subject of rebooting mathematics. So Doron will argue that much of infinitary mathematics is meaningless. In his view, it is an accident that so much of theoretical mathematics developed before we thought carefully about computability and computing machines. In Doron's view, a differential equation is the degenerate case of a finite difference equation. As he likes to point out, calculus was originally developed by Newton and Leibniz in a rather intuitive fashion, before we had the machinery of epsilon delta arguments that was developed by Bolzano and Cauchy over 100 years later. The next speaker will be Madhu Sudan, and he'll speak about communication amid uncertainty. So much of communication theory assumes the sender and recipient have a completely shared context, that if a message gets through and is successfully decoded, it is completely understood in the way the sender intended. But what happens in the messier circumstance when the sender and recipient do not have a completely shared context, so that we do not understand each other's words in precisely the way intended? Further, how does communication take hold with virtually no shared context? And how can communication be used to extend the shared context between communicating parties? Madhu will present a mathematical framework for understanding these issues. And following these talks, just like yesterday, we'll have a Q&A/panel session from 1:30 to 2:15. Then we'll have a series of speakers in the late session, beginning with David C. He'll be speaking about Byzantine consensus through the lens of information theory. And a famous theorem states that no blockchain network can support dynamic participation and remain safe under temporary network partitions. This is what is called the availability-finality dilemma. In his talk, David will describe a new class of flexible consensus protocols called ebb and flow protocols, which support a full, dynamically available ledger in conjunction with a finalized prefix ledger. The finalized ledger falls behind the full ledger when the network partitions, but catches up when the network heals. Then Mary Wooters will give a talk entitled Fun Facts About Polynomials and Applications to Coding Theory. As everyone knows, given any 3 points, one can find a parabola through them. If the 3 points are collinear, then the parabola is degenerate, it's self-aligned. Secondly, if you look at any vertical slice of a paraboloid, you get a parabola. Mary's talk will be about related but lesser known facts. Given fewer than 3 points worth of information, what can one say about a parabola going through those points? Then, in analogy to the paraboloid fact, are there surfaces other than paraboloids that you can slice and always get parabolas? Mary will answer these questions and discuss applications to error-correcting codes. Following Mary, Petros Drinius will speak about randomization in numerical linear algebra and approximating the log determinant and the von Neumann entropy. The introduction of randomization in the design and analysis of algorithms for matrix multiplication, regression, singular value decomposition, and so on has provided a new paradigm for numerical linear algebra. In this talk, Petros will discuss how such approaches can be used to design fast algorithms for approximating the log determinant and the von Neumann entropy. Then Lydia Zekentho will speak about reasoning about generalization via conditional mutual information. Lydia will tell us about a new notion that she and her collaborator, Thomas Finke, have developed that provides a framework for studying the generalization properties of machine learning algorithms. Their new notion is based on conditional mutual information, or CMI, and quantifies how well the training data can be recognized given a trained model. Bounds on CMI give different types of generalization guarantees. Then following Lydia's talk, we'll have a second Q&A and panel session just like yesterday, and that'll go from 5:15 to 6 p.m., which will wrap up the day. Okay, so in preparing my remarks for today, I had some concern about the fact that we were waxing relatively philosophical in our discussion of mathematics. But after last night's presidential debate, I thought, well, can't get any worse than that. So in some of the early talks, the speakers will describe philosophies of mathematics that are influenced by information theory, computational paradigms, and what we're learning about the physical world. A question to ask ourselves and the speakers are these issues merely matters of armchair speculation, or could they have real-life consequences? So we have the following interesting and important observation. Given a limitation on the number of bits in any real-life computer, and that these bits can be used to express just finitely many different things, there is some smallest inexpressible positive integer. And moreover, beyond some point, all positive integers become inexpressible. There will therefore be number theory questions that we can barely articulate in the given number of bits, let alone solve. As you might ask, what about some of our most cherished theorems and open problems? Through this lens, some theoretical questions and even some landmark theorems may turn out not to be meaningful. And I stress the word may. Again, it may turn out to be meaningful, but maybe not. Questions like the P equal NP question, or even Gödel's two big theorems, the completeness theorem for first-order logic and the incompleteness theorem. It's conceivable that this question, the famous P equal NP question, and these landmark theorems, they may in fact not be meaningful through this lens. And we need to put these questions and theorems more carefully under the finitist microscope. Okay, so as you might be able to tell from now, I'm a bit of a radical finitist, and we'll hear from two other such finitists in the first two talks. And I would like to suggest two new pillars for finitistic mathematics. The first one is that mathematics should be built up from the foundational concept of a bit, rather than from the traditional foundational concept of a set. The second one is that the real numbers should be thought of as evolving processes involving the generation of binary digits, whether they be the result of measurements, calculation, or even definitions. For example, the continuing binary sequence 0.010101 and so on. They should not be thought of as completed processes or completed sequence of digits. Thus, there is no meaning to talking about the full decimal expansion of pi, or even the full expansion of 0.010101 and so on. So to think about, it may turn out that the axiomatic development of mathematics was in a certain respect wrong-headed, based on ill-conceived notions of points and lines in the case of Euclidean geometry, or what it means to be a set in the case of axiomatic set theory. Finally, a challenge. The establishing of meaning in metamathematics and mathematics should be put on firmer ground, using a formal information theoretic paradigm. Even the mathematical formalist, one who views mathematics as symbol manipulation with no fixed interpretation, reverts to describing the rules for the symbol manipulation informally, with the hope that there is no room for ambiguity. How do the symbols become more than marks on a page? How does meaning and shared understanding take root, and how can it be formalized? So Madhu will be actually talking about this from a mathematical point of view. Okay, so I'm going to talk about this first pillar. So the replacement of the notion of a set as a foundational concept with that of the bit. So the classical formal development of mathematics proceeds from the notion of a set. Following von Neumann, we let 0 be the empty set, 1 be the set containing just 0, in other words, the set containing the empty set, 2 the set containing 0 and 1, and so on. So again, 0 is the empty set, 1 is the set of 0, just containing 0, or the set of just the empty set. 2 is the set of 0 and 1, so then the set of containing the empty set, and the set containing the empty set, and so on. And in this fashion, we build the natural numbers. From there, we built the integers, the rationals, the reals, and so forth, and even the infinite von Neumann ordinals, as they're called. But the question, isn't the bit a more natural building block for all of mathematics than the set? The rules of what constitutes a set are inherently squishy. Probably all familiar with Russell's paradox, for example. But the bit, the presence or absence of a signal, seems inherently non-squishy. Since we can do computer proofs in all sorts of areas of mathematics, even areas that make extensive use of infinitary mathematics, I should add, we have an existence proof that the bit is a workable alternative building block for all of mathematics. In fact, programming languages like Python and Java have simple-to-use set classes, showing that it is a simple matter to define the notion of a set in terms of the notion of a bit. So for a discussion of the second pillar, in other words, the development of the real numbers as this evolving sequence of binary digits, we're going to turn to our next speaker. And if you're interested in a more detailed account of the current thesis, I recommend you look at my paper on the archive called the Finitist Manifesto: Do We Need to Reformulate the Foundations of Mathematics?